it's great to be speaking at the seminar. Thank you for inviting me. I appreciate it. So yeah, so my talk is about the intersection between reasoning and deep learning, and about what deep learning is still missing and how we can fix it. So I'll talk about 5 simple things. So first, I'll talk about generalization. What is generalization? What's important? Then I talk about the nature of abstraction and the relationship between generalization and abstraction. Then I talk about the role of deep learning in this picture, what forms of abstraction deep learning can generate, and where it fails. Then fourth, I'll talk about the methods that are currently working to generate the kinds of abstractions that are currently out of reach for deep learning. And finally, how can we leverage a hybrid approach to reinforce the strength of each method while compensating for their respective weaknesses. So you should expect a very high-level talk, actually more of a philosophy talk than a technical talk. It's really just my own thoughts about these questions, no more than that. So let's start by talking about generalization. And as everyone here probably knows, AI has been getting more and more intelligent lately, right? I mean, look at all these breakthroughs, especially the breakthroughs in the past 5 years, which were all powered by deep learning. You know, self-driving, playing StarCraft or Dota at experiment level, playing Go at experiment level, being able to generate text, even potentially code, and so on. No matter what the task, we seem to be able to achieve above human level performance if we put our minds to it. Our minds, that is. And some people today are arguing that solving all these different tasks mean that we're on the verge of achieving general intelligence, that we're on the verge of creating an algorithm that will be able to perform any task at human level or above, solve any problem, an algorithm that will have the same generality as human intelligence. And of course, you know, such a creation would have infinite value. Why not? So you should give these guys billions of dollars. They can make you very rich, infinitely rich, in fact. And these are all real quotes, by the way. It's not bad. And the truth is, the things we've been doing with deep learning are remarkable engineering achievements. Like a decade ago, no one could have foreseen that you could do so much by just fitting big curves. However, none of this actually brings us 1 inch closer to generality, in the same sense that, you know, in the 90s, Deep Blue was superhuman at chess, but that did not bring us closer to general AI. We're still exactly as far to generality in AI today as we were 10 years ago. And that's because there's a big difference between task-specific skill and general intelligence. Skill or behavior is the output of a process, and that process is intelligence. Intelligence is a skill acquisition process, or behavior generation process, which is basically the same thing. And there's a big difference between a process and its output. It's like the difference between a car and a car factory. And buying a car does not actually mean you've solved the problem of vehicle manufacturing. And in particular, modern AI, deep learning-based AI, has stark limitations that reveal it's not close to generality. In fact, it's not even close to being flexible. It's very data hungry. We can solve any task, but that requires a dense sampling of every possible situation that pertains to that task. And it does not really withstand contact with the real world very well, because the real world is very variable, very, you know, always changing, very surprising, very uncertain. And if you need to have been exposed to every possible situation in advance, then you're not going to be able to deal with the real world. In the same way, our deep learning models are very brittle. They are sensitive to small perturbations. They only work on data that stays extremely close to what they've been trained on, what the programs have been programmed to do. So here are a few concrete examples to illustrate this. Take self-driving, for instance. Self-driving is a pretty well-scoped, constrained problem, and we have millions and millions of hours of driving data to train our models. So you would think that we'd be able to do something out of it. And as a matter of fact, our best models today are largely not deep learning based. They are mostly based on heartbeat rules. They are based on symbolic models of the world that interface with the world. They are deep learning. But even these models, they are only, you know, L3 to L4, and L5 is decades away. And the approach of trying to train deep learning models to drive a car end-to-end from sensors to actuators has been a completely failed approach today. Another example is a couple of years back, OpenAI trained a superhuman DOTA 2 AI, and it was trained on a restricted version of the game on about 50,000 years of training data. And then when it was actually released, when you could actually play against it, it was very quickly defeated in a systematic way by non-champions in a matter of days. So it required a humongous amount of data to be trained, and it actually turned out to be very brittle. In the same way, domestic robotics seems like a fairly simple task if you're anywhere close to general AI, but it remains nowhere to be seen. Being able to handle the variability of different kitchens in different houses is completely out of reach today. And so what has led us to this state of things? Let's talk about the shortcut rule, which is a well-known principle of system design that says that basically, if you start optimizing for a specific metric, you will take shortcuts along every possible dimension of your problem that is not captured by your metric. And this is very similar to overfitting in machine learning. A simple illustration of this effect is seen in Kaggle competitions, where participants optimize for the evaluation metric of the competition only. And as a result, the systems they create cannot be used in production settings because they took shortcuts along every other dimension, like computation requirements and code maintainability and so on. And in AI, what the shortcut rule means is that if you focus on achieving task-specific skill, you will achieve task-specific skill, but you will do so by taking shortcuts. And you end up with a system that does not display generalizable cognitive abilities, because skill is orthogonal to generalization. So in one way, if you can generalize, then you can develop new skills by going from the general to the specific. But in reverse, there is no path from the specific, from task-specific skill to generality. And it's not really possible to come up with a specific task or a specific metric that would actually require broad generalizable ability. If you fix the task, then you open the door to shortcuts. A famous story in AI is the story of Alan Newell. In 1973, he proposed that the field of AI should start focusing on chess, because chess in humans features memory, learning, reasoning, analysis, and so on. And so surely if we can solve chess, then we should be able to understand all these cognitive mechanisms. And as a matter of fact, we did solve chess eventually. And when we did, it turned out not to teach us anything about human cognition, like the alpha-beta algorithm at the heart of Deep Blue is completely orthogonal to human cognition, to all the cognitive abilities that humans leverage when they play chess. So because we had fixed the task, we took shortcuts to solve it. And the modern version of this story is to increase skill on a problem like StarCraft, Dota 2, self-driving by adding more training data. And by adding more training data, you are reducing the need for generalization, because you cannot do anything generalizable. So you solve that by removing the need for generalization. It's always possible to create shortcuts to solve a given task without featuring intelligence, without requiring generality or generalizable cognitive abilities. You do that by reducing novelty and uncertainty, by injecting new information about the task, either as priors, as hard-coded rules, or as training data. And in the limit, you can achieve arbitrary skill on arbitrary problems without requiring any generalizable cognitive ability at all. So you can always use deep learning, or even just a big hash table to solve arbitrary tasks, but that requires either a tremendous amount of manual modeling, hard-coded rules, or a tremendous amount of training data. And so the obvious example is learning to play Dota 2. So as I was mentioning a couple of years ago, OpenAI trained a system on 50,000 years of gameplay, and that system was able to play at superhuman level in some respects, but in the end it was brittle. People figured out very reliably how to beat it. and it could not adapt to simple rule changes. If you add a very simple rule change to the game, like say, hey, towers can insta-kill now, any human player can adapt to this in 0 shot instantly. But the AI will have to be actually retrained because it significantly modifies the dynamics of the gameplay. And so you would require thousands of additional years of data if you wanted to fine-tune the system to adapt to a simple rule change until the next small variation shows up. And in the real world, small variations and new rules show up absolutely all the time. So it's important to remember that it's always possible to create shortcuts to solve a given task without featuring intelligence. And that's really been the history of AI for many decades. You take different problems like chess or Go, and you find ways to solve these problems extremely effectively, but without displaying any intelligence. And I like to quote Descartes on this. He wrote something 400 years ago, which I think really captures the essence of the difference between an intelligent agent and an automaton. And that quote, predates the rise of AI by several centuries, obviously. In fact, it slightly predates the first mechanical computers, because the first mechanical computer was the Pascaline, which was invented by Pascal. And at the time this book was published, he was only 14. So it was 5 years before he invented the first mechanical computer. And what Descartes tells us in this quote is that an automaton is going to operationalize abstractions that were provided by its creators. And on the other hand, if you are intelligent, you're able to produce your own abstractions, and so you can adapt to arbitrary situations. And the automaton can only handle situations that match the abstractions that were given to it. And it's the adaptability that characterizes intelligence. And I want to stress that the generation of autonomous abstraction, which is to say intelligence, is really orthogonal to encoding and operationalizing pre-existing human abstractions, which is what we're doing in current AI systems. We're building systems by taking our abstractions and turning them into programs, either via training data or via hard-coded rules. We are not creating systems that are capable of developing their own abstractions the way we do. And intelligence is very much the ability to autonomously produce your own abstractions. And that difference is akin to the difference between creating a cartoon character or creating a new life form. A cartoon character can only play the scenes that you drew, that you taught it to play. Whereas, a life form is actually independent, can actually adapt. And that's true whether you draw the cartoon scenes by hand or whether you use motion capture. And in this analogy, training data for deep learning models would be analogous to motion capture for cartoon characters. And yeah, so what I really want to stress is that the task-specific skill exhibited by a system tells you nothing about its intelligence, tells you nothing about its generalization power, because generalization is a relationship between what you can do and the information that you have, your priors and your experience. And it's always possible to buy skill for a system that has a given level of intelligence by providing it with more information about the task, which reduces uncertainty and novelty, and thus reduces the need for generalization. So you can always increase skill without increasing generalization power by reducing uncertainty and novelty with more experience, more priors, more trained data. So skill does not characterize intelligence. And as long as we target skill in our research, we will not obtain intelligence because the shortcut rule applies. We are not making progress because we have the wrong target, because we are targeting task-specific skill. Instead, we need to start targeting generality itself, generalization. So what's generalization? You probably already know about it, at least informally, but broadly it means the ability to handle situations or tasks that differ from previously encountered situations. So fundamentally, it's the ability to deal with novelty and uncertainty, and that's precisely what you need intelligence for. And since generalization is defined in terms of novelty and uncertainty, one thing to note is that novelty and uncertainty themselves, they should be defined with respect to a certain knowledge referential. So you can distinguish between two forms of generalization. There's system-centric generalization and developer-aware generalization. And system-centric generalization is the ability to adapt to situations that the system itself did not previously encounter. And developer-aware generalization is the ability to adapt to situations that the creator of the system, the developers of the system, could not have anticipated, which is adaptation in a much stronger sense. So system-centric generalization is a definition that relies on maybe to machine learning, but it's a much weaker form of generalization compared to developer-aware generalization, which is what we should actually be targeting. Developer-aware generalization is synonymous with autonomy, the ability to adapt to novelty without the help of a human engineer. And if you want to achieve human-level domestic robotics or human-level self-driving, this is actually what you need. And here's what's really important to understand about generalization and the nature of generalization is that it characterizes the relationship between the information that you have and your operational area over the space of potential future situations that you might encounter, which are going to feature novelty and uncertainty. And generalization can be quantified as the efficiency with which you operationalize past information in order to deal with the future. So you can interpret it as an information conversion ratio. And that can give you a quantified definition and measure of intelligence. And if you like equations, you can use algorithmic information theory to precisely quantify it. So I wrote about it in a paper, but that's beyond the scope of this talk, so you can just check out the paper if you're interested. Yeah, so one thing I want you to keep in mind is that generalization is not a binary property of a system. There are not systems that can generalize or not generalize. It's actually more of a spectrum. And you can characterize AI systems by their level of generalization. On the very lowest end, you have software systems that don't have to adapt to past experience because they're purely static systems operating in a world without novelty, without uncertainty, like chess playing. And then the second level after that is robust AI, which corresponds to the statistical learning definition of generalization. It's robustness to known dimensions of variability, like the ability to handle a new sample from a known static distribution. And all of machine learning falls into this bucket. Then you have flexible AI, which is the ability to handle a broad domain, including the ability to deal with situations and tasks that if you want to do self-driving, then that's the kind of AI that you're building. And finally, you have extreme generalization, which corresponds to open-ended intelligence. So a system that's capable of adapting to arbitrary domains, arbitrary tasks that the creator of the system could not have anticipated. And today that's exclusive to biological intelligence, obviously. And an interesting property of this spectrum is that it mirrors the history of progress in AI. In the early days, we are mostly looking at problems that did not involve generalization, purely algorithmic problems. Then we started seeing the rise of machine learning, which was concerned with local generalization. So generalizing to a new sample from a known static distribution. And recently, we are starting to look at systems that can deal with the variability and uncertainty of the real world beyond machine learning, because the real world is not a static distribution. The future is constantly new. And so we are looking at self-driving, domestic robotics, and so on, and we are making baby steps. And eventually, one day, we may be able to create truly open-ended systems capable of the same level of generality as humans and animals. That's the dream, even though we are very far from it. Another interesting thing we can note about this spectrum of generalization is that it mirrors the structure of human cognitive abilities. If you look at theories of the structure of cognitive abilities, like the Kettle-Horn-Carroll theory, for instance, they describe cognitive abilities as a hierarchy with, at the lowest level, you have task-specific skills, which correspond to local generalization. Then you have broad abilities, which mirror broad generalization. And finally, you have the G factor, which corresponds to open-ended generalization or general intelligence. So that means that, in short, if you're interested in measuring generalization power, you should not look purely at skill. You should control for priors and control for experience. And if you're interested specifically in comparing artificial intelligence to human intelligence, then you should standardize on a shared set of priors. And that should be human cognitive priors. You basically don't have a choice. And human cognitive priors is something that we call core knowledge. And if that sounds interesting to you, you may be interested in the abstraction and reasoning corpus, which is a kind of intelligence test that's meant to be used by humans and machines that I released some time ago in 2019. It's very similar to Raven matrices like IQ tests. And you can also see it as an input-output program synthesis dataset. And a key idea is that in this dataset, every task you see is new. It only shares abstract similarities with other tasks. So you're controlling for experience because you're doing few shot program learning, typically just from two or three examples. And you're controlling for priors because the tasks that are featured are grounded purely in core knowledge. It's not supposed to involve any acquired knowledge, like language, for instance. So all the tasks are constructed on top of four knowledge priors, which are objectness, elementary geometry and topology, numbers, and agentness. So yeah, maybe we can talk a bit more about core knowledge. So core knowledge is basically the set of innate cognitive human priors that are possessed by humans and that guide our ability to learn throughout our lives, in particular at the beginning of our lives, but throughout our lives in general. They form basically the atomic building blocks of thinking. So this is based on work that was done primarily by Elizabeth Spelke from Harvard, and she identified 6 different core knowledge systems. There might be more. I mean, this is very much ongoing work. And these core knowledge systems are innate, or at least we're able to acquire them very, very early in the first few months or years of our lives, and universally, meaning that every human being is going to acquire the same systems. And they are very ancient. You will find them in non-human primates. You will also find many of them in different animals, in birds, for instance.
Francois?
And, yeah.
Yeah, just I've seen similar discussions, and causality is often counted as a core. Where does that sit in this list?
Yeah, so causality, that's, yeah, you can definitely consider it part of core knowledge systems, absolutely.
But it's not contained within one of the ones on the list, or
yes. You basically put it either in agentness or elementary physics.
Okay. Okay, thanks.
So agentness in particular is a concept that agents pursue goals and do things in order to obtain certain results in a causal fashion. Yeah, so basically, I was saying, so ARC tasks are grounded purely in a certain subset of core knowledge. And we ran a Kaggle challenge on the ARC datasets in early 2020 that produced a bunch of interesting solutions that were all based on program synthesis. And right now, the state of the art is roughly 30% of tasks solved, which is pretty good, actually. It's not a lot, but it's pretty good. Okay, so by now, you should have a pretty good idea why we should focus on achieving broad generalizable abilities instead of task-specific skill. And that brings us to the problem of abstraction. Abstraction and generalization are closely tied because abstraction is basically the engine through which we produce generalization. An interesting observation about the universe, and that applies to pretty much any problem domain you can think of, is that the universe is made of many different things that are all similar, all analogous to each other. We are surrounded by isomorphisms, and I call this the Gladoscope Hypothesis. So you know what a kaleidoscope is? It's basically a tube with few bits of colored glass, and these bits of colored glass are repeated and amplified by a set of mirrors. And that mechanism creates a remarkable richness of complex patterns out of just a few kernels of original information. And generalization is the ability to mine the experience that you have to identify bits that are reusable. Then you extract these bits and you call them abstractions. They take the form of programs and representations. And then you can use these abstractions to make sense of novel situations. And how do you identify reusable kernels of structure? Simply by noticing when two things are similar, by noticing analogies between things. If something is repeated twice, then both instances must have a single origin, like in a kaleidoscope. And intelligence, or generalization power, is literally sensitivity to abstract analogies. And that's in fact all there is to it. So if you have a very high sensitivity to analogies, you will be able to extract powerful abstractions from little experience. And you will be able to use these abstractions to operate in a maximally large area of future experience space, which is the definition of being intelligent. So you'll be maximally efficient in converting past experience into the ability to handle future novelty. I was just saying abstractions could take the form of representations and programs. And that's a reference to two key categories of abstractions. There's value-centric abstraction and there's program-centric abstraction. And they're pretty similar to each other. Both of them are about comparing things and merging individual instances into shared abstractions by eliminating certain details about the original instances. But there are key differences. And the key difference is that one operates over a continuous domain and the other operates over a discrete domain. Value-centric abstraction is about comparing things via a continuous distance function. So it involves comparing two instances of an object or expressing an instance in terms of prototypes, which are basically abstract features. It's similar to human perception, human intuition, pattern cognition. And on the other hand, program-centric abstraction is about comparing discrete programs, so that is to say discrete graphs. And instead of computing distances between instances, you are looking for subgraph isomorphisms. You are looking for exact match, not similarity. And you are looking for exact match of a subset of the structure. And that is similar to human reasoning. This is what software engineers do. Like if you hear a software engineer talk about abstraction, this is what they mean. They don't mean similarity, they mean subgraph isomorphisms. And these are two qualitatively different forms of abstraction. And so both of them are driven by analogy. There are ways to compare things and draw analogies between things. But value analogy is geometrically grounded. You compare instances with a distance function. You create abstractions by merging instances that are similar into a prototype. And program analogy is topologically grounded. You compare the structure of two graphs and you create abstractions by merging instances that are isomorphic into an abstract program. And all intelligence arises from a combination of these two forms of abstraction. So you can remember them via the left brain versus right brain analogy. One half is for perception and intuition, and the other half represents reasoning, planning, mathematics, and so on. So with the caveat that, of course, it's a metaphor. It's not actually the way that brain lateralization works, but it's a poetic image. It also mirrors the type 1 thinking versus type 2 thinking distinction, by the way. Okay, so it's time to talk about deep learning now. Deep learning excels at the first form of abstraction, value-centric abstraction, which makes sense because deep learning models are continuous. In fact, they are differentiable. They're big differentiable parametric models. So it's very intuitive that they would be able to produce abstractions that are grounded in geometry. They are geometrical machines. And in supervised deep learning, what you are doing is an analogy between two spaces. There's an input vector space and there's a target vector space, which is usually much smaller. And you are learning a smooth geometric morphing between these two spaces, point by point, via gradient descent. So you are performing geometric analogy in continuous space. Deep learning is about relating samples to each other via a learned distance function, and implicitly this learned distance function between samples defines a manifold. And you can contrast this with the second kind of abstraction, which is grounded not in geometry but in topology, which is all about comparing the structure of subgraphs and finding subgraph isomorphisms and abstracting them. So going back to value-centric abstraction, it relates to the manifold hypothesis in machine learning. So the manifold hypothesis posits that all natural data lies on the low-dimensional manifold within the high-dimensional space where it is encoded. And as far as we know, this is pretty much accurate for any perception problems. It's true for MNIST digits, like in this example, obviously. It's also true for human faces, the sounds of human voice, even natural language. And the manifold hypothesis implies that within one of these manifolds, it's always possible to interpolate between two inputs. And by interpolate, I mean morphing one input into another via a continuous path along which all points on the path fall on the manifold. That's basically what it means for data to lie on manifold. And the ability to interpolate between samples is the key to understanding generalization in deep learning. It is the reason why deep learning works. If you have data points that can be interpolated, then it means you can start making sense of points you have never seen before, which is generalization, by relating these points to other points that lie close on the manifold. So in other words, you can make sense of the totality of the space using only a sample of the space, as long as it's a sufficiently dense sample of the space. So a deep learning model is basically this very high dimensional curve with some constraints on the structure, which originate from architecture priors. And you're fitting this curve with gradient descent. And that curve has enough parameters that you could really fit anything. If you train your model for long enough, it will effectively end up purely memorizing the trained data. It's not going to generalize at all. But the thing is, the data you're fitting to, it forms a highly structured, low-dimensional manifold within the input space. And because the fit of the curve happens gradually and smoothly over time, which is a consequence of the gradient descent process, there will be a transitive point during training at which the model is roughly approximating the natural latent manifold of the data. And the curve that's learned by the model at this point will come close to moving along the actual, the natural manifold of data. So the model will be able to make sense of new inputs via interpolation. And one thing that's important to keep in mind here is that the power to generalize in this setup is much more a consequence of the natural structure of your data than it is a consequence of any property of your model. I mean, the two properties of your model that matter is that it's continuous and you're fitting it incrementally. But you will only be able to generalize if your data actually follows the manifold hypothesis, if the points can be interpolated. And obviously, the more informative and the less noisy your videos are, the better you'll be able to generalize, since then your input space will be simpler and better structured. So this is a setup that is very, very effective for perception problems, but it has limitations. It's very brittle, it's sensitive to small perturbations, as we mentioned. And that's because we are doing a mapping point by point between two spaces. So if you shift one of the spaces slightly, the mapping that was learned starts breaking down. And by the way, that's why topology-based abstraction is actually more powerful than geometry-based abstractions, because distances are not robust to small perturbations, but structure can be robust to small perturbations. So topology is what underlies robust and flexible abstraction. And there's an even bigger limitation than brittleness, which is that for this geometry-based abstraction to even be applicable, to even be relevant, you need to be dealing with a continuous domain. You cannot apply deep learning to discrete problems, like sorting a list, for instance, or finding prime numbers, or actually 99% of all software engineering. You cannot solve these problems via continuous optimization because they have a fundamentally discrete structure. And of course, you could try embedding their discrete structure in a continuous manifold, but that would be very artificial because you could not use that manifold for interpolation because that's not the natural structure of the data. So your continuous parametric model would not generalize to things it has not seen before. So it would be a continuous embedding, but it would not be a useful continuous embedding. If you wanted to make it actually useful, you would need an exhaustive sample of the problem space. You would need to basically memorize the entire problem space. Okay, so big takeaway here is that in order for deep learning to even be relevant on a given problem, you need two things. First, you need your problem to be interpolative in nature. So you need the manifold hypothesis to apply. Otherwise, deep learning simply cannot generalize. The ability to generalize for deep learning comes from the structure of the data, not the property of the model itself. So that's true for lots of problems, in particular any perception problem, but not all problems that we care about. And the second thing that we need is that you need enough data to learn the manifold. And that's usually a lot of data. You need a dense sampling of the distribution that you're trying to learn. And one interesting thing about the ARC dataset is that lots of people have tried using deep learning on ARC, including using very large pre-trained models like GPT-3. And no one has managed to achieve anything with it because ARC problems are not interpolative in nature. And you only have a few examples per task anyway. So it just doesn't work. On the other hand, program synthesis is very effective on the ARC dataset. So Jeff Hinton had a quote in the MIT Tech Review last year. It was saying, deep learning will be able to do everything. And that's not entirely true. I think deep learning is going to be able to solve problems that only require value-centric abstraction. It's not going to be able to solve problems that require program-centric abstraction by nature, because it's not what it does. And so anything a human can solve via perception and intuition, you can probably do with deep learning, assuming you get a big enough data set. But anything that requires reasoning, planning, program-centric abstraction, you cannot do with deep learning. So how are you going to solve these problems, like ARC problems, for instance, or sorting a list, or finding prime numbers, and so on, like any reasoning or planning problem? And the answer is program synthesis, which is to say combinatorial search over graphs of operators taken from a domain-specific language, a DSL. So it's basically discrete search over graphs, as opposed to continuous optimization. And there are many different flavors of that, like agentic programming and so on. And you can actually draw an analogy between machine learning and program synthesis. In machine learning, your model is a differentiable parametric function. In program synthesis, it's a graph of ops. In machine learning, your learning engine is gradient descent. In program synthesis, it's combinatorial search. And in machine learning, the key obstacle is that you need a dense sampling of your data manifold. In program synthesis, the key challenge is combinatorial explosions, that you have so many different programs to consider. So you can use program synthesis to solve problems from very, very few examples, which is why it's effective on ARC. But the set of possible programs you can build grows combinatorially with program size. So it's been super effective on ARC. Also, obviously these are just baby steps. So these numbers are a bit outdated. Today, the state of the art is more like 30%. But all these solutions basically leverage the same template. And if you want to use, whether it's continuous optimization like deep learning or program synthesis, if you want to use them in practice, you need to make them efficient. And if you want to make something more efficient, there's a universal recipe you can use. You introduce modularity and hierarchy, and you introduce reuse. And reuse is very much just another word for abstraction. And that's basically universally true. So of course, this is true for continuous optimization. If you apply these principles to continuous optimization, you obtain deep learning. Deep learning is what you get when you add modularity and hierarchy to continuous optimization. That is to say, when you structure your parametric function into deep stacks of layers. And further, if you start hard coding abstract modular use in continuous optimization, you get certain deep learning architecture patterns like convolution, for instance. Convolution is a hard-coded module which abstracts away spatial position, so it's abstract with regards to location. Likewise, RNNs. RNN is a recurrent neural network. It's a module with a temporal for loop. So it hard codes some kind of abstraction with regard to time axis. And so this recipe of making something more efficient by introducing modularity, hierarchy, and reuse, obviously it also holds true for discrete combinatorial optimization. So you can limit your search to programs that follow software architecture best practices, which tend to revolve around modularity and hierarchy. And then you can start to introduce function reuse, which is the second type of abstraction I was mentioning, program-centric abstraction. So in general, there are two key tools at your disposal to make program synthesis efficient: abstract function reuse and making smarter branching decisions when you are searching over program space in order to fight a combinatorial explosion. And you can actually use deep learning there. So let's talk briefly about symbolic modular use, which is to say program-centric abstraction. So the general idea is that you start with a given domain-specific language, you run program search to solve various problems like arc tasks, for instance, and you generate solution programs. And then you start noticing subgraph isomorphisms, both within a program and across different programs. And you're going to abstract these subgraphs away into reusable functions. You add them back to the DSL. And that's actually super similar to software engineering best practices and to library reuse in the open source world. And that's a very important way to make program synthesis more efficient. But there's also a complementary and even more powerful way to improve program synthesis, and that is to merge program synthesis with deep learning, to leverage deep learning as a way to reduce the search space, the program search space, and to fight combinatorial explosion. And I was mentioning that deep learning was basically useless on arc type problems, but that's not entirely true. The fact that it doesn't work yet doesn't mean it's going to be useless. I think it has a role to play. I was saying that all intelligence is a combination of two forms of abstraction, the continuous form and the discrete form. And I really believe you cannot go very far with just one of these options. You need to combine the two to achieve the true potential of intelligence. And I think that's what human intelligence is extremely good at. That's what makes humans special, that we combine perception and intuition together with explicit reasoning. We combine value-centric continuous abstraction with program-centric discrete abstraction. So I mentioned that in order to do deep learning, you need two things. You need an interpolative problem and you need lots of data. So if you look at a single arc task, it's not interpolative and you only have 3 examples. So it really doesn't match the requirements of deep learning. But if you take a step lower down the scale and you look at core knowledge priors, the core knowledge priors that the arc tasks are built upon, each of them is interpolative in nature and could be learned from data potentially. And of course, you can collect lots of data about them. So you could use deep learning at that level. You could use deep learning as a sort of perception layer that parses the world into discrete objects. And if you take a step higher up the scale and you look at the space of all arc tasks, then again, you will find continuous dimensions of variability across programs. So you can leverage interpolation to some extent, and you can use deep learning there as well to produce intuition over the structure of the space of tasks and the structure of the space of possible solution programs. And reasoning in humans is often driven by high-level intuition. And that's the key to address the fundamental problem of program synthesis, which is that the complexity of the search process grows exponentially. And there are 2 exciting research areas to combine the strength of deep learning with the strength of program synthesis. So first, you can start looking at discrete programs that incorporate deep learning components, like making deep learning models part of the DSL. And second, deep learning models that inform the discrete search process and that improve its efficiency. Program synthesis today uses lots of heuristics. Usually you can replace hard-coded heuristics with a learned heuristic with a deep learning model. So of course, this assumes that the space of heuristics is a manifold on which you can acquire descent, but we have pretty good reasons to believe this is true. So you can use deep learning as a perception layer to parse the situation into discrete building blocks, and then you can feed these building blocks to a discrete search process. And you can use deep learning as a driver, as a guide for program synthesis that will give you new blocks to add to your DSL, and that will give you intuitive program sketches to guide your search. And I believe in the future we'll move towards hybrid systems that will combine deep learning and program search. It will be mostly discrete program search under the hood, but that search will be driven by deep learning. And that leads us to a long-term vision for the future of AI and deep learning. And that vision closely resembles the workflow of software engineers today when they're developing software. So if you want to know how AI will operate in the future, I think you can just look at how human engineers, software engineers operate today. Engineers constantly manipulate abstract programs that were developed on a different task than what they're currently doing. And that's the sort of abstraction that is the holy grail of AI. And AI will be moving along these lines, along the lines of creating new programs from an existing global library of abstract primitives shared across many different problems. And so you will have, a lifelong string of tasks. You can imagine the arc tasks, for instance. And for each task, you'll be able to assemble a task-specific solution that will involve deep learning perception modules, like for parsing objects in the task, for instance, but also algorithmic modules for reasoning. And the search process will, of course, be driven by intuition provided by deep learning models. So you cannot really say that deep learning is going to be able to do everything, but you could say that deep learning is going to be involved in the various different solutions that we will develop to various different problems within the field of AI. Okay, so in summary, what I want you to take away from this kind of long and sprawling talk. So first of all, generalization is really the key to make progress in AI. Like not task-specific skill, we should not target task-specific skill, we should really target generality itself. And abstraction is how you produce generalization. And abstraction is very much about mining your past experience, noticing things that are similar, like performing analogies, and then turning these analogies into something that's reusable. And that reusable thing is an abstraction. And there are two types of abstraction, and each type is produced by analogy making, obviously. So there's a fundamental relation between abstraction and analogy. So one is based on the value comparison, continuous value comparison. One is based on exact structure matches. And the type of abstraction deep learning performs is value-centric abstraction. So it's a very good fit for perception problems. It's a bad fit for reasoning problems. If you want to do reasoning, you need discrete program search. You need to be able to leverage an algorithm that's actually capable of performing program-centric abstraction. And when you do this, there's a big obstacle, which is combinatorial explosion. So it's the problem you need to solve. And I believe in the future, hybrid systems in AI will use deep learning as a way to help address combinatorial explosion. And that's going to be very similar to how human reasoning is heavily guided by perception and intuition. Like if you set out to prove a theorem, for instance, you're not going to be kind of considering every possible path in operation space the way program synthesis engine would. You start out with already some intuitive sketch of where you're going to go and what are the big stepping stones that you're going to leverage on your way. And that's why that intuition structures your explicit reasoning, and that's what makes your reasoning process efficient. Okay, that's basically it.
Well, thank you. It's really interesting. Do we have questions from the audience? Matthew Farrell.
Yeah, thanks. I wanted to ask if you had any comments on these quantized variational autoencoders, which have a generative model that's sampling from a distribution that takes on discrete values. Is that related in any way to this idea of solving discrete problems?
Yeah, so one thing to keep in mind is that using discrete codes in a deep learning model does not fundamentally change the nature of deep learning. What you're going to be doing is that you're going to be finding ways to embed your discrete symbols into continuous manifold. And that will only work is your discrete symbols are basically if they're structured, if they actually lie on an interpolating manifold. If they do not, like if you look at prime numbers, for instance, which have no sort of continuous structure, it's not going to work at all. So there's really a qualitative difference between discrete systems and continuous systems. And of course, you can try to embed a discrete system into continuous space, but that's not going to be effective.
Thank you.
More questions? I see a question on the chat, which I think you did answer in your talk from Tom Wang. What is the current state of the art on ARC? And you did give a slide with 20% result.
So in the Carol competition that we ran last year, it was over 3 months with a $10,000 prize. At the end of the competition, the best results were like 18–19%. And now there's been new developments, and now it's slightly below 7. It's like 29 or so.
Yeah.
But they all use the same basic template. They're all doing discrete program search.
Let me ask a question. So it's going to be a little vague, but I'll try. So the deep learning has again, many of the ideas are actually fairly old by standards in this field, and it's because they're sort of standard mathematical ideas, such as optimization by gradient descent, for example, taking derivatives and doing back propagation. And so to oversimplify your talk, you're sort of saying that has its place, and then program synthesis, which was really a very core symbolic AI topic, also has its important place. And then there is, of course, a theory in AI, many search algorithms, a great deal of discussion of the structure of search, of the structure of heuristics, programming language theory. And I'm perhaps speaking a bit as a physicist, but it seems like a much more diverse terrain of ideas and techniques. And do you feel that they all have their place within intelligence, or do you feel that there's some simplification of this subject of program synthesis, which we should be discovering?
I do believe we are still very early days in program synthesis, in the same way that 20 years ago we are very early days in neural networks. And most of the big breakthroughs are still to be done. And most of the big breakthroughs, I would say intuitively, they're probably not going to come from hard computer science or from mathematics. They're more likely to come from finding smart ways to apply learned heuristics to improve the search process. So I expect, the genetic programming is obviously a very promising way. Guiding program search via deep learning models is also a very promising way, like trying to map out the space of all possible interesting programs and embed it on the continuous manifold, and so on. I can expect, most hard computer science improvements you could have done have already been done in the 70s. The low-hanging fruit has already been ripped in a way. And the new breakthroughs will probably come from areas that no one has really been looking at so far.
Okay.
But yeah, I do believe both discrete search and continuous optimization have a very important role to play, that we will not end up with a unified system that only leverages one of them. For instance, you could say, hey, deep learning is going to be able to do discrete reasoning. Of course, you can embed discrete constructs into continuous spaces, but that's not effective. It does not really work. In the other way around, of course you could do continuous, embedding, representing continuous spaces as a discrete structure, or doing continuous similarity comparison between instances. You can do all these things with discrete programs. I mean, after all, computers obviously operate on discrete symbols, and you can do linear algebra on computers, so it works. But there's really, techniques that are a good fit for problems and techniques that are a bad fit for problems. If you try to use program synthesis to build an MNIST classifier, it's going to be a disaster. And in reverse, if you try to use deep learning to develop a list sorting program, it's also going to be a disaster. It's not impossible, it's going to be a disaster. So you should really use program synthesis for discrete search, and you should use gradient descent for continuous problem for perception.
One might be able to define, or at least characterize this dichotomy between the deep learning, the continuous and the discrete in some way, which isn't necessarily in terms of the mathematics of continuous and discrete, which are, again, can approximate each other. So, for example, just one of the simplest ways in which logic and language and programs are different from the continuous world is that you can put a single knot into your logical formula and to change everything. So a tiny change, will have a drastic effect, which tends not to be the case on problems that you can solve using continuous methods. But let me ask a different question, which is, if you've looked at the OpenAI recent Codex release, and if what you perhaps have comments about that and its relevance for what you're saying.
Yeah, so Codex basically uses a language model to kind of interpolate code snippets from Stack Overflow and GitHub. It is not a program synthesis engine. It is not performing program synthesis. I believe a tool like Codex can have its value in the workflow of software engineers. It can make your workflow as software engineer incrementally more proactive, in the same way that you've probably used autocomplete in Gmail. Like Gmail will suggest sentences to complete your emails. That actually saves potentially several seconds. And in the case of programs, using a very smart autocomplete or using multiple suggestions, that can save you potentially even more time. It can also replace looking up Stack Overflow entirely, so it can save you probably entire minutes. But it's more of a UX UI question. It is not program synthesis. It is not.
Okay. Let me. I think I understand why you say that, but for clarity, because one might look at it and say this is a program synthesis. So what is the definition of program synthesis that it is not performing?
I mean, it's not program synthesis in the way it works. I mean, it generates code, but it generates code via interpolation. It's just a language model.
Well, it is just a language model, but again, the words program synthesis, if we don't try to define them, then it is. I think. I mean, clearly.
Sure. I mean, the difference is in program synthesis, you are performing search over a space of programs which are graphs. Right. You're not like generating word by word or character by character a string that is plausible.
Right.
When as a software engineer, when you write code, you are doing program synthesis, because you have a mental model of what the program actually does, how it executes like. You're not just stringing words because, well, I mean, sometimes you are. Sometimes you just look something up on Stack Overflow, you copy and paste it. That's basically what Codex is doing. But that's not a very effective way to write programs, actually.
So there is a program synthesis where you must contain testing and combinatorial structure of the program and refinement.
It must contain some model of the execution, some model of what the program does. There's a distinction between what the program looks like, which is the string of words, and what the program represents, which is an execution graph.
I mean, I can point out that the codex does have a very minimal form because, of course, its actual success rate is very low. The transformer gets maybe 1 or 2% success rate, and then it needs to scan many times to find one that works. And it does test that it works, but it is a very primitive program synthesis from that point of view.
So I don't think success rate is a tricky metric. My main issue, even if it were 100% accurate on the sort of problems that you find on Stack Overflow, I would still not say it's a program synthesis engine, because the only thing it does is interpolate from stuff that's on Stack Overflow or GitHub. If you present it any novel problem, it will completely fail. And that's kind of the point of programming, is to solve novel problems. That's the point of intelligence, is to be able to adapt to new situations. And that's why, like GPT-3, for instance, can actually solve very basic IQ test-like reasoning problems, complete this string of numbers, for instance. But it's entirely ineffective on arc tasks, even though by nature the arc tasks are not very different. What's the difference? Was it effective in one and not the other? It's because for the very basic IQ test-like questions, it has seen them online. It's just memorized them, or at least it's memorized something that's a template of the thing that is that can actually generalize to new instances. With Arc, they're all novel. All the tasks are novel, so it has not seen them online, so it cannot do anything. So it is not intelligent because it cannot adapt. It cannot deal with a new situation.
Right.
Like taking all the knowledge out there and encoding it into a program, that is still not intelligence. This is tremendously useful. It's very powerful. You can do tons of things by just encoding and operationalizing existing knowledge and abstractions. But there's a category difference between this operationalization and intelligence, which is the generalization of new abstraction to deal with new situations.
Right.
And until you have the second one, you will not be able to actually deal with the real world, with the wide west of programs in the wild and cars on the road and coffee machines and kitchens in the wild.
Right. Makes a lot of sense. Okay, I'm going to try to go in order. So, Tony Tong Wang, you had your hand up.
Yeah. I was just going to ask. By the way, I really enjoyed the talk, Francois. When exploring these hybrid systems that can both do like value-based reasoning and like program-based reasoning, like aside from ARC, what are like good tasks to explore these systems on?
So any task that is discrete, and when you're able to generate new instances that are fundamentally different from the past instances that you've seen. So you should fit your discreteness and novelty. Does that make sense?
Yeah. I see. Thanks.
Okay. I have a question from Kenneth Bloom, if you'd like to ask it, or I can read it from the chat.
I haven't opened the chat.
He's just saying, please read.
Okay. So what are your thoughts about the best approaches for program synthesis via neural networks? Ideally, something better than a hybrid. Humans do reason using neurons.
Yeah, so I was mentioning in the talk, when you do difficult reasoning as a human, you're not just considering, explicitly considering all the steps one by one. You start out with an intuitive sketch of where you're going, and that sketch is a form of pattern recognition. The fact that it is possible, and so by the way, so the human brain is extraordinarily slow and limited. It reacts, on the order of 50 milliseconds, which is very slow. It can only you can perform reasoning chains in a very short amount of time, and there's only a very limited sequence of neurons that could possibly fire in that amount of time, because they just don't have the time to fire in sequence. But somehow we are able to solve extremely complex problems. That strongly suggests that we're able to take a path in solution space that is extraordinarily efficient. When you look at an arc task, for instance, the space of possible programs you could apply to the objects you see is extraordinarily large. You're talking about millions and millions of programs. But yet, when you look at your R task, in your mind, you're only considering 2 or 3 different possible solutions. So you manage to radically prune the space, and you've done that without thinking about it. If you're not thinking about it, it's not reasoning. So you've done that via pattern recognition, via intuition. And I think that's kind of what we should be doing with deep learning models. We should learn very large embeddings of the shape of program space and task space, and then use these embeddings to basically radically prune the search space to just say, hey, I'm going to need this stepping stone, and I'm going to get to this result. And instead of considering 1 million programs in your discrete search process, you only consider 100.
Okay, thanks. More questions from the audience?
Francois, once again, thanks so much for a wonderful talk. Tony, myself, others, we worked on your art task. We had a lot of fun working on it. So thank you so much for creating that data set. Just wanted to get your thoughts on, so if, do you think of, have you given any thoughts on creating an art like data sets, but it's not for images, but maybe for either for text or for sound? I mean, have you thought about that kind of data sets? Just wanted to get your thoughts on that.
So I really like 2D grids of symbols for some reason. I have kind of this unspoken hypothesis that the human brain does reasoning in 2D. So that's why I tend to gravitate towards 2D grids instead of like strings, for instance, strings of symbols. That said, you could convert arc tasks to 1D strings. But yeah, I'm more interested in 2D grids. So no, I have no plans to switch to just 1D strings or sounds or something else. I do have plans to expand the arc data set, but it's still going to be very much in the same format.
I see. Sure. And then, you talked about sort of different level of general AI and then going all the way up to open-ended AI. So do you have some thoughts on how we might get there?
Yeah. As I was mentioning, the first important thing is to be asking the right questions and to be setting the right targets. Because as long as we set the wrong target, we're going to achieve the target and then realize it was the wrong target all along. That's the shortcut rule. If you define a metric, you're going to achieve your metric, but in doing so, you're gonna take all the shortcuts possible. And at the end of the drawing, you realize that actually you're missing what you cared about. And so one thing that's very important is to start evaluating results on benchmarks on which the tasks that you see at test time are truly novel. They are truly novel. They are not like anything you've seen in the training set. And that's the primary goal of ARC. It's to be a kind of game that you cannot practice for. No matter, like in theory, you could generate for yourself 1 million ARC tasks, train deep learning model on that. But still the test tasks that you're going to see are not be like the ones you generated yourself. So that's the first idea. And the second idea is, as I was saying in the talk, I really believe we are going to, in human intelligence results from these two kinds of abstractions that are enmeshed, that are supporting each other. All of your thoughts, all of your, even when you're doing something that's very hard reasoning, like proving a theorem, for instance, or when you're doing something that's very perception-oriented, like you look at a scene and you understand what it contains, it's not actually pure perception. It's not actually pure reasoning. It's actually very much a combination of the two on every level. And with deep learning, we're entirely focused on one half of the picture. So we only have one hemisphere of the brain. If you want to get to general AI, we really start to leverage both of them, both kinds of abstraction at the same time in ways that could support each other and unlock the limitations of each other.
Sure. That's it. Thank you.
Great. Let me ask one last question. So a topic that I find quite interesting, and we've had quite a few talks last year, is interactive theorem proving and using AI and machine learning to help automate interactive theorem proving. We sort of looked at Christian Zegedi's group is doing, groups at OpenAI and elsewhere. What do you think about that as a serious test of generalization ability?
Yeah, I think that's very promising, and I definitely want to see more of that.
Okay. Okay. So if there are no further questions, let's all thank Francois for a very inspiring and illuminating talk. And we'll have next summer, as I mentioned, at 2 o'clock next Wednesday, and it will be J.M. Landsberg of Texas A&M will speak about matrix multiplication and its analysis using techniques from algebraic geometry. So I hope to see you all there. Thanks.
Thanks a lot.
Thanks, Francois.
Thank you.
Francois, I wanted to ask